Hey everyone, this is part 2 of our EECS 280 Project 5 walkthrough series. In this video, we'll be overviewing the Map.ADT component of Project 5. This implementation builds off of the binary search tree.h file, so if you haven't already, go check out our EECS 280 P5 BST walkthrough video. This video will help you conceptualize how a binary search tree functions and walk you through some of the specific implementations. With that said, I'll be explaining how we're going to implement a map abstract data type using a binary search tree under the hood. So let's get started. For this project, we're representing a map as a binary search tree. Taking the definition from the C++ documentation, maps are associative containers that store elements formed by a combination of a key value and a mapped value, following a specific order. Some important things to note are each element stores a pair instead of a single item, keys are unique, elements of a map are sorted by key, and values in a map or value in a pair can be accessed by key using the bracket operator. And remember, this is all going to operate like a binary search tree. Before, we might have conceptualized our tree like this. So each node corresponds to a single datum, and that datum could be of type int, char, etc., and our tree is sorted. Now we need to think of our tree like this. So each node corresponds to a pair. Note that we still have a single datum, but that single datum is a pair. The first item in our pair is our key, and the second item in our is our value, and they don't have to be of the same type. However, all keys are the same type, so here we have all keys of type string, and all values are the same type for our tree. So here all of our values are of type int. Also note that our tree is sorted by key. Let's go through an example of creating and modifying this instance of a map. Our end goal of creating this map.h file is to be able to create map objects. Imagine we're reading in a txt file and we want to create a map to keep track of every word we see and how many times we see that word. Here we have the map variable word count. Map string int means our keys will be of type string and our values will be of type int. Under the hood, our map is a binary search tree. When we create a map object, its tree won't have any data in it, so the root pointer will be null. If we see the word blue 5 times in our txt file, we might want to insert the pair blue and 5. To do so, we can use this curly brace notation, with the key first and the value second separated by a comma. This is one way to create a pair. Another way to create a pair would be to create an instance of the pair class from the standard library. Pair has public members first and second that can be accessed using the dot operator. To set our key and value, we can do the following. So note here that we've declared a pair called tuple, and we can set its first or key value to apple using the dot first and using tuple dot second to set our value of the pair to the integer 1. So now we can insert this pair object into our tree, where it will become a datum for a node. This syntax is accomplishing the same thing as the curly brace syntax. We could also insert an element into our map using the bracket operator. When we use the bracket operator on a key that doesn't exist in our tree, the new key value pair gets automatically added to our tree. We can also modify existing key value pairs by using the bracket operator. Let's say we count another instance of apple in our txt file. To increment its count, word count apple returns a reference to the value in the node, and we can then use the plus equal operator to modify the value directly from the integer 1 to now the value 2. Okay, now that we've established what a map is and how it more or less works, let's hop over to our map.h starter file. So the first thing I want to point out here is that we have 3 template parameters for our map. We need to specify the type of our keys, the type of our values, and our comparator type. In the previous example, we only included the key and value types because our comparator is default set to the standard library's less, which we can see here with the standard library less. So this less is a functor that utilizes the less than operator to compare 2 keys. In our example, when we inserted the pair apple1 into the tree, less was used to determine that the string apple is less than the string blue, and so the pair would be inserted somewhere on the left branch. But what if the type of our keys wasn't something that the less than operator could be called on? For example, in our map compile check.cpp, we create a map whose keys are of type duck, which is the class we've created here at the top of the file. So note specifically on, where is it? There we go. Line 39, here is a instance of a map called duck map with the types duck, string, and duck wealth less. So when we create a map whose keys are of type duck, using the less than operator between two duck objects wouldn't really make sense here because we haven't overloaded the less than operator and ducks don't evaluate to a numerical comparison. So we've implemented this functor type here for you called duck wealth less on line 20. And when instantiated, it can take in two duck objects and make a meaningful comparison. So let's take a look at this functor in more detail. So the main idea of a functor is that we have a class that works like a function. When we create an instance of duck wealth less, let's call it less, we can make the object behave like a function call by overloading the call operator and passing in parameters. The call operator we see here takes in two duck objects. For this example, assume we've declared two ducks, duck1 and duck2, with wealths of 100 and 500 respectively. When we call less on these two ducks, the overloaded call operator will return true. When we're setting our map's key compare type to duck wealth less, we're telling our map, this is how we want keys to be sorted. Remember though, that our map is really just a binary search tree that stores key value pairs. If we want to implement this map using our binary search tree.h implementation, we need to write a comparator that can compare two pairs. This is why we have pair comp in our map.h file. We want our tree to see two pairs and compare them based solely on the key value. If we don't create a custom comparator, the built-in behavior would compare both the keys and values stored in each pair. So let's say we have two pair type objects, one with duck1 as a key and noodle as a value, and another with duck2 as a key and doodle as a value. Our pair comp is going to be really similar to the implementation for duck wealth less. We're going to overload the call operator just like before, but this time we'll pass pair type objects as parameters. Just like we used duck wealth less to compare two duck values, we'll need to instantiate our key compare type to compare our keys in each pair. So if we had a map with types duck, string, and duck wealth less, under the hood, it would really look like this. And our binary search tree would store pair type data and compare data using pair comp. So now that we've overviewed some of the concepts behind our map structure, let's add some code to our map.h file to help get you started. So first I want to go to instantiating the tree that is the under the hood component for our map here. So if we go to line 115 of our starter file, it says add a binary search tree private member here. So let's do just that. And remember, we'll need to make our datum of type pair type, so we can hold our key value pairs. And then we need to compare them using our pair comp custom comparator that we will implement next. And you can just call this whatever you want for the variable name. Now let's go implement our custom comparator. So remember, with a class, we can have both private and public sections. And since we want to create an instance of key compare and only our class will be using that, we can declare it under private. So I'm just going to write some pseudocode here. So we'll have an instance of key compare. Then we need to also make sure we are overloading our call operator like so. And again, don't just copy this verbatim, but implement it yourself. And this will return the comparison made by our instance of key compare on our pair 1 key and our pair 2 key. So think about how we can access those values or those keys from our pairs. Okay, awesome. So in terms of these other functions here, these will all heavily rely on your binary search tree implementation. So for example, if you want to know if your map is empty, all you have to do is check if your tree is empty. So think of the functions you implemented in your binary search tree.h and utilize them here. Also, when trying to determine whether or not we need the big three here, consider these questions. Is our map directly managing dynamic memory? Are we using the keyword new or delete in our map.h file? Who is responsible for the memory on the heap? Our tree, our map, both? These are some things to think about when implementing your map. As a final note, when you implement the driver program, you will not be using this map.h file. Instead, use map from the standard library. For more information on the driver program, check out our next video, the EECS280P5 driver walkthrough. Alrighty, that's all I have for you, so best of luck on this project.